announced today, I'm going to talk a little bit about pathfinding on the Lightning Network, and some part of it will be about the gossip protocol, which is like a little bit of a review of what the gossip messages are going to look like. So it's a little bit basic again. But other than that, I've been told that you seek more for like opinionated talks and recent ideas instead of like how the bolts work, because you already know all of that. So I'm trying to go a little bit more in this direction. Yet I'm still an educator, so we're going to do a little bit of education. So the outline is I will start with a quick recap of the 2018 Lightning residency, as I was a resident at that time, so I thought I share a little bit of my experience with you. Then I'm going to compare IP routing with routing on the Lightning Network. Christian already mentioned a couple of things on that. Then I will go through the motivation of why pathfinding is actually a difficult problem on the Lightning Network. And then I'm going to talk about actual pathfinding strategies. In the middle, I talk a little bit about gossip, and I forgot to put it in the outline. Actually, I had it in the outline, but I was shifting topics, so yeah. So yeah, this was the picture of last year's Lightning residency. So the quick recap goes like this. It started with Christian explaining me that routing is a hard problem, and then there was Elaine, who actually told me that routing in practice always fails, and then we had Christian again, who explained me that routing can be difficult and relies on channels and capacity and peers being online. And then there was Jack Mellers, who, if you read it correctly, was talking about autopilots and the channels won't be relevant, so he touched this topic of this is difficult. And this is what I got out of the residency, that routing is bad problem. As we discussed yesterday, this is plain wrong. Routing has been solved on the Lightning Network. It's actually pathfinding that is the hard problem. So I want to be a little bit more precise on the terminology that I'm trying to use in this talk. So the good thing is, I want you. I want you because these are open problems and you can make a huge difference on them. Right? I would currently say that we don't have a working solution for pathfinding on the Lightning Network. There's many proposals out. We already seen some yesterday. And I will go a little bit through them again today. So especially for these people staying in the summer and wanting to work on Lightning, I think this is a great opportunity because there is also, really the chance to make a huge difference. So I want to motivate you to tinker about these problems. All right. Why is this not working? I just use this one. So as I promised before, like really going into pathfinding, let's compare IP routing with onion routing in order to understand this. So let's do a quick recap of how IP routing works. I think most people are familiar with this. A node processes the IP header of the IP package that it receives, and then it extracts the sender and the recipient of this package. Actually, it would not necessarily need the sender for forwarding it, only for response in IP. And then it dissects the IP address of the recipient into the network part. And the network part, is usually the first couple digits or bits. And it's a hierarchical address scheme, right, which the network uses for making routing decisions. And then there's the host part of it. And a router looks up the network part in its routing table. And if the network is known, then it sends the link to sends the package to the next link via the link layer protocol. So for example, Ethernet or DSL or whatever link layer protocol there's implemented. And otherwise, it will send it to its default route, which is something like, hey, you probably know better how to handle this. But this is pretty much how IP routing works. And the routing tables themselves, they are dynamically updated, for example, via the border gateway protocol. I think there's several variations of those. But there's basically some communication among internet hosts and internet routers that basically talk to each other all the time and share information about the topology of the network, of where networks are located, and then they can make decisions of where to forward this package. And the concept, how I always call it, is called best effort routing. Christian always uses the word distance vector routing. I think that's in computer science terms the more precise term. But as you can see from my shirt, I'm a mathematician, so please forgive me. And I would say this is an amazingly strong concept. I mean, if you think about it, the internet is just running all the time. And if you talk to the people who came up with TCP/IP, I think maybe they're just humble, but what they usually say is, we didn't expect this to scale that much, right? They were doing just a research project for university, and then it took off and people were just implementing and building on top of it. And I mean, basically, yes, we had this address-based dilemma, but to some degree it's scaled to infinity, right? It's one of the strongest, stable computer systems that we currently have. And I just want to like make it one last time like explicit of how it really works. Like there's the address of the IP package that states, I want to go to Chaincode Labs. And what the router does is it says, oh yeah, that's in New York because this is what it reads from the host part. And then it says, I sent you along this road because this gets you closer to New York. Ask again later. Right? And when you go to the next crossway or next router, then you can repeat the process basically. This is how information is being sent on IP. And this is actually pathfinding, right? The network finds a path. So I want to compare IP routing with onion routing, or at least with onion routing, how we use it in the Lightning Network. So the first type, as we already mentioned, in IP routing, we have this method of called best effort routing, because every router basically has its best effort to say, the best thing I can do is send you along this road. Where in onion routing, as we discussed several times, we have the source-based routing. The sender has to make all the decisions about what path to use. And then the data format is very different, because in IP we have open headers. Everybody along the path can read the header information, whereas in Lightning we basically have encrypted headers. There's only a small part of the header that gives a hint of what you should do at your hop, but the rest of the entire information is encrypted and be hidden away from you. The sender and the recipient are known to the routing nodes, so they can use this information to help with the routing, to make decisions. Whereas in onion routing, I think it was Fabrice yesterday who had this really, I think some people already mentioned it to me, and for me it was also eye-opening, of saying, it's really funny, the routing nodes don't actually need the gossip protocol and the gossip store to some degree, because they are just going to forward the package anyway to their peers. They don't even have to be aware of the topology of the network. And then in IP routing, we have an address space that is logical and hierarchical overlay network. And to some degree, I would argue it reflects some geographical properties, right? I mean, the IP networks that you usually have are usually located in some direction. It doesn't have to be like this, but usually when you make a request, you route geographically in your country or in your region. You don't necessarily go over China unless you use something like Tor or so. Whereas in the Lightning Network, it's really a fully decentralized peer-to-peer network. The addresses, are just public keys and curve points, right? They don't give you any information of that, and we don't have this address space in that sense. Then when you talk about the edge weights of the network, in IP, I would argue that they're mostly static, right? You have the bandwidth of the links. That is basically the information that you need for routing. A package arrives, and then you say, oh, I can actually forward it on this link, or this is what you could use to make routing decisions. If you look at the routing table protocols, they might use this and say, hey, this is less hops, but the hops are really slow, so I'd rather take a longer route where I can actually really push through traffic. Whereas in Lightning, it gets really strange with the edge weights. It's first of all not even clear what to put on the edge weights, but I would argue it's highly dynamic. Right? The fees can change, or another edge weight that you should use for routing is actually the balance. Right? How much money is in this channel, and not in the channel, but on your side of the channel, because that's the only, that's a necessary condition to be able to forward a package. Right? And this thing is changing all the time. With every routing process, this thing gets updated. So if you think about the topology and information propagation, the network in IP can react to changes of the topology pretty well. So we have this border gateway protocol, and if some router fails, or if we just switch some cables, routing tables are being updated. It takes some time, but since the network is fault tolerant, we might find some other routes. It's still working pretty well. If we look again at this like fully decentralized peer-to-peer network, we have a gossip protocol, which is rather slow. It's noisy to propagate all relevant information. Right? So for example, if you think about the balance, let's consider we ignore privacy for a moment, and we just want to propagate the balance of all channels at all the time. This would be a mess because it's changing with every payment process. Right? So it technically is probably not even possible to achieve this, right? But then again, we want to have privacy, so we might not even want to share this information. Right? So this entire topology and information about how the network looks like in Lightning, we don't have this. Then if you think about denial of service attacks, in TCP/IP you can do spoofing. I mean, I can just send out an IP package and say it comes from a certain sender, and then the nodes will reply to this. Since everything is open, since we have open headers, the ISPs can actually monitor some behavior like this and can interfere with this and can mitigate these attacks. Whereas in Lightning, everybody or anyone can just send and delay onions, and this is pretty much impossible for us to detect or to mitigate, right? So if you're running a Lightning node and I want to be nasty, I just gonna send some onions away, don't put a lot of payload in it in the sense of like Satoshis that I put in the HTLCs, but I can fill up your payment channel. As you know, you can only have 483 HTLCs concurrently in flight. And I make a circular onion to myself, and I just don't reveal the payment hash. And for the next 24 hours, your payment channel is completely locked. And currently, I would say we don't even have any. I mean, I'm looking at you, but we can't prevent this in Lightning. We can just hope nobody does this because there's an economic cost attached to it, right? You need to have some capacity or liquidity in order to do this, but you can do it rather cheaply, right? So maybe a market emerges where people say, I don't accept too small HTLCs, right? But that is all stuff we don't know yet, right? And then if you really look at pathfinding itself, like from all these properties coming, it's basically just a summary. In IP routing, it's collaboratively done by the network. And this is, to me, if I think about it, a really amazing achievement that people came up with this. I'm not even sure if they were aware of this, how strong this property was when they built this. But it's really this distributed network that solves this complicated pathfinding problem in a really beautiful manner. Whereas in Lightning, it's achieved by the sender or maybe a third-party pathfinding service, right? I mean, might happen. I would argue that this is going to be a business model for reasons we can discuss offline, but we don't know yet. Okay, so seeing that table, you probably already have a pretty good feeling of why pathfinding is hard in the Lightning Network. I just want to elaborate on this a little bit more. So the key ingredient for routing is to know a path. And in an ideal world, pathfinding is really easy. I mean, we create a graph, or we know the graph from the gossip store, and the nodes are the Lightning Network nodes, and the edges are the payment channels, like we expect this, right? And then the weights might be the routing fees. And there's a label for the edges called the balance, because that has to be respected to some degree. And then finding a path is just as simple as calculating Dijkstra algorithm on the network. Every computer science student learns this, I think, everywhere in the world. I hope so. So you can basically take this information from the gossip protocol, and you can compute the cheapest path and just create an onion and go out and send it. And then one constraint, that's why I called it constraint, Dijkstra problem, is the labels should be respected, right? If there's not enough balance, then you cannot do this. And after computing the Dijkstra algorithm, either you find a path because the network is fully connected and you can actually have it, or we know that no path exists with enough balance, right? Because the edge ranges labels didn't work out, and yeah, then you know this too. But the Reality Check is a little bit different. So first of all, the weights, are they really the routing fees? I would say they change with the payment amount and over time, right? Depending on, like, if I really build the graph as a data structure in my computer, I have this in memory. Depending on the payment size, the fees and the weights that I use for the Dijkstra problem are actually changing because I have this fee rate, which makes it a little bit complicated. And also, people can announce to change their routing fees. Then there is no label for the edges, right? I mean, technically, yes, when you forward the onion, when you selected a path, the onion might come back, right? You remember you have this telescope metaphor from Christian of saying you start setting up all the HTLCs, and at some point there is not enough balance there and everything goes back to yourself. So it's private, it's highly dynamic property. So this is really an issue. So we can't really respect these labels when we are selecting a path, right? We can only try it out and probe it. And then, of course, we don't. So even after we compute the Dijkstra algorithm and we try all the paths and the path didn't work, we don't know that no path with enough balance existed. because what could have happened is I try a couple of paths, they don't work, I try other paths, and meanwhile the network has changed all the balances in the channels, and one of the first paths might have worked through after all, right? So we actually, when we don't find a path, we don't know that we can stop the routing. Technically, we should try again and again and again. It's a little bit theoretical here. And what we do is we probe for paths until we find one. And I mean, currently we have public, maybe 10,000 nodes on the Lightning Network. I didn't look up the number, but it's a very small graph, so we can actually afford to do that. But if we want to use the Lightning Network as a scaling solution for Bitcoin and the Lightning Network really grows, we run into problems when we probe for paths all the time. And yeah, I think I said this before. So it's a highly dynamic problem with a lot of uncertainty, right? That is what I want you to remember. And this is really a problem that needs more brain power to be solved. So I talk a little bit about the gossip protocol because this is really the part of the Lightning Network that helps us to make some routing decisions. I try to make it quick because it's basically just what's written in the bolds. So the purpose of the gossip protocol, obviously routing a source space, and nodes need to be aware of the topology of the Lightning Network, which nodes exist, how can I connect to them, and how to open a channel with them. I mean, I need some information in order to actually operate these. And then what are the channel policies, right? What are your routing fees? What are the HTLCs you're accepting? Is there a minimum payment? Is there a maximum payment? What can I do with you if I want to use your channel? And yes, I think I have this twice on the slides now. And then, of course, you want to like share this information with your peers, right? So because it's a peer-to-peer protocol, you peer with somebody and then you share the information you know about other channels with others, and you need some like mechanisms to do this. So there are 4 announcement messages on the gossip protocol, and they're all Lightning messages, so they're all encrypted via the noise XK protocol, as we saw before. There's the announcement signature messages. They are needed to negotiate if the channel shall become public or not, right? As we discussed yesterday, both parties have to agree when a channel is open that the channel is supposed to be public. If I don't announce my signature for this channel and you open a channel with me, you cannot make this channel public. I mean, you can announce it, but nobody on the gossip network would forward this channel or accept this because there's my signature missing. So then there is the actual channel announcement. So this really makes the channel publicly known to the network. So as soon as you have these signatures exchanged, you can actually go out and announce the channel. And it kind of like proves ownership of the channel because you have signatures attached to it. So you cannot just like, as a denial of service attack fighting mechanism, you cannot just go out on the gossip protocol and say, hey, by the way, this is a channel. Then your peers would not forward this. You need some proof of ownership that you and your channel partner are actually the people who maintain the channel. And then there's node announcements. So this shares some metadata of the node, for example, its IP address. And I mean, that's a tricky one. I think tomorrow we're going to have a discussion section about privacy on the Lightning Network, on the gossip protocol. And therefore, I already want you to take this into consideration, right? Because I mean, this is information that's also easy to double check because you can just like peer with this node and check if there's really Lightning node running on this IP address. And now you have a mechanism to connect Bitcoin addresses to IP addresses. And this is, in my opinion, a huge intrusion into your privacy. And the interesting thing about node announcements on the Lightning Network, they are only possible if at least one channel was announced publicly. This is, again, a measure to fight denial of service attacks, because otherwise I could just go out and say, hey, I'm a Lightning node, and I sent this message like 1,000,000 times, and then the gossip protocol would have to do a lot of work. So nodes will only forward these messages if at least one public channel was announced and verified to this channel. And as we need signatures, these public channels can only exist, as you know, with a funding transaction. It's part of the announcement message. So you need a blockchain transaction, right? So this really takes away some spam. And then there are the channel update messages. And what they do is they update the channel policies, right? So once the channel is announced, we only know there is a channel of a certain capacity, right? All these hard data, but everything that is flexible, like the fees, the amount of HTLCs we accept, or the minimum HTLC amount, all of that part is part of the channel update message. Okay, I would skip the details of how these messages look like, because I think you can just read them up in the bold. So I'm just running through these slides. Yeah. Yeah. Right. You need to. Yep. Okay. So, okay. All right. Meanwhile, I should have tapped this button. So when I would talk through this slide pretty quickly. There's actually no message on the gossip protocol for deleting channels from the network. So the way how you delete in nodes, not only nodes, but channels in particular from your gossip store, is you basically look if the funding transaction is spent. Right? And then you know the blockchain tells you this channel doesn't exist anymore. Yeah, well, we don't have splicing yet. But once we have splicing, we need to think about these things probably. And then, of course, you can also, thinking about privacy with gossip and stuff that is related, you can, for example, see the channel lifetime on the blockchain. And maybe now you are able, if the node opens other channels, to connect channels or connect Bitcoin addresses again, right? Maybe somebody was using the same wallet to run several Lightning nodes, so you can even merge Lightning nodes. So weird stuff can happen. Now you can have friendship of IP addresses and yeah. And then there's another part of gossip messages that exist, and these are the queries for the gossip protocol, right? I mean, one thing was just the announcement and forwarding information, but nodes can retrieve old gossip messages from their peers. I mean, question to you, why would this be useful? Why do we need this?
Those are going offline and online if they miss gossip messages.
Yeah, for example, if a node goes offline, it misses some stuff, right? So it wants to like get a reason for another reason, an even more basic reason. What's the other reason why we need that? Bootstrapping, right? If a node comes online for the first time, the node wants to make a payment, source-based routing, it needs to know what the network looks like. So it needs some way of asking the peers of like, hey, what is the network actually looking like? So there's queries basically for short channel IDs and reply short channel IDs end messages. And what they do is basically you ask for channel announcement and channel update messages for a specific channel. Of course, this is not really of use yet if you don't know the short channel IDs. And that's why I think you have these queries where you have the channel range and reply channel range messages, right? So one is ask for channels in a certain range, and the range is the block height. So you say from block 500,000 to block 600,000, please give me all the short channel IDs that you know, and then come reply messages that basically tell you these are the short channel IDs. And then you can do the other query and ask for channel announcement and channel update messages, right? So you can pull these information from your peers. And then there is the gossip timestamp filter. So now you can only have channel updates that have a certain timestamp. So you don't want to have all the old channel updates, right? You only want those that are like most relevant. All right. So what I do from all these messages, I have a quick summary of information that can be used for routing and pathfinding. So there's basically the CLTV expiry delta, which basically says if you want to route over me, this is how many blocks the HTLCs I want to lock in order to make sure everything works. You have the minimum and maximum HTLC amounts that you are accepting. A short channel ID, of course, you need this information because on the onions you need to like put in which short channel you're using, and then there's the fee rate and the base fee, right? Remember, every time you route through a node, you have a certain amount of fee that is fixed that they want to be paid, and the fee rate is basically looking at how much money are we forwarding, and then a fraction of that is also put into this. And yes, I also included the channel flags, which are direction and availability of the channel. So there are some flags in the messages where you can, like, when you turn off your node, basically make an announcement of saying channel update, hey, now we're offline. Don't use this channel anymore. I mean, it also takes some time until this information is spread, but it's useful information to take this away. And then, of course, so for example, flags. So for example, there's this option channel HTLC max, which says how many HTLCs do I accept on this channel. Something like this, right? If there's a channel that only accepts 20 concurrent HTLCs, you might not want to use this for routing. So yeah, this is all the information that we have. And what I would argue is basically taking into consideration the first part of this talk, this is not really a lot of information. I mean, some information, and of course you can like maybe get some other information from elsewhere, but it's not a whole lot of helping me as a source to make qualified routing decisions.
Does that actually help you? If all the k-shortest paths go through one channel, and that's the channel that is dying, you can throw away your entire result.
Yeah, so yes, I agree. But at some point in time, there will be paths that are more expensive going through another channel. So of course you can like use a different algorithm or adapted version with the more information you get back. So yes, I'm not saying we should use this algorithm, but I was saying if you probe for paths, and the only thing you do is you start with the shortest path because you want to save on fees, right? I mean, the notion of short here is also tricky. I mean, you could also say short in order of hops that you're doing, and then you do just breadth first search.
I'm just wondering if computing k-shortest paths is not more expensive than just doing the single shortest one adaptively over and over again.
Probably it's better to do the single shortest path adaptively, but still it's an expensive algorithm, right? And you do it over and over again. So yeah.
So I agree that the k-shortest paths is a really good solution if you have some really expensive piece of service that you're talking to, and the latency to talk to it is probably expensive as well. But if it's located right next to your actual node, then it might be cheaper to do the adaptive.
Yep, no, I agree. But in any case, I mean, we discussed this yesterday already. If you're running Lightning on your mobile, and your mobile is supposed to do this for a graph, I mean, let's plug in some numbers, right? Let's say, I don't know, let's take 1 million nodes and a reasonable amount of channels that are coming with them, and you multiply these two numbers, you get like a lot of computational steps. It's getting ugly pretty quickly. So it's pretty inefficient and hard to compute on a large scale. On Lightning Network, and in particular on mobile devices, maybe one of the reasons why I'm suggesting that pathfinding might be a service that is being outsourced, where you just ask a pathfinding service to give you a path, or we could outsource this by having the network finding a path for you, which would mitigate the trust issue here a little bit, or increases your privacy to some degree, because if you ask a third-party service, the third-party service at least knows that you want to pay a certain person on the network. And yeah. So if all nodes behave well, a single path should be quick, maybe 1 second, to do it independently of the network size, right? I mean, this is if everything is like nice in pathfinding and routing. The problem is, if nodes misbehave, probing can take a pretty long time. Because as we learned yesterday, we should not try to pay a second time if payment doesn't work, right? And while probing a path, we could actually end up in this scenario where something maybe hit the chain, or maybe there's just some timeout. We don't know what the node is doing. HTLCs are being set up, but you don't get anything back. You don't know what's going to happen. So you're going to wait like really, really long for one probing attempt, right? It's not a computationally heavy problem on your side. No. So considerations with AMP, and it's a little bit like trash talking this right now. It's not in the sense of like I'm not a fan of AMP, but I want to like point out the problems, right? So there are advantages. I refer to Alex for them, and he already mentioned some of them. But the idea, as we know, it's basically a known fact that larger payments have a higher likelihood to fail. I mean, you can simulate this very easily. You can try this out. You can use your own data. You can do whatever you want, but you will. I mean, it's basically common sense, right? At some point in time, some channels just are less likely to have enough balance for you. So what you could do is you can split larger payments into several smaller payments and send them along various routes. So what are the disadvantages of this strategy, in my opinion? Well, one thing is the routing time increases drastically. Because in atomic multipath routing, still we need to probe every of these smaller paths, right? And we already saw that probing might take a really long time. So now let's... No, it's that. It's the maximum time for each path. Because the pre-image by the end of the day is only going to be revealed when enough incoming capacity over all HTLCs is there. So now comes the problem. If I'm probing one path and this path is just misbehaving, I don't know what to do. I'm just waiting. Right? And now it's getting even more messed up, because different paths that I'm probing might have different CLTV expiry times, so stuff gets really ugly.
I should probably mention that what you're referring to probing is what I call a payment attempt, and I use probing differently.
Probably in the sense that I was using. So finding the root, and I'm probably wrong, but finding the root is just 10 times more work, but actually trying it is your worst case.
No, so the thing is, in atomic multipath routing, I can concurrently actually try those routes.
Right.
Right? So this is not the issue here. The issue really is that if one of these routes takes a really long time, all the other routes have to basically wait because they don't settle independently of each other.
Let's say so larger payments are more likely to fill, and using more nodes is more likely to cause a problem. Is that
True. Yeah. This would also be a rule of thumb, right? And in AMP, what we're doing is we're decreasing the amount to pay, but we're decreasing the amount to pay, but we're increasing the amount of nodes that we involve. And yeah, this is bad. As we just discussed, probing is still necessary for every path. Then also the base fee is paid several times, right? So AMP is also more expensive. Side note, do a lunch discussion with me about the fee model in Lightning, because I would argue that we should actually get rid of the fee rate, because a lot of the data science part makes a lot more sense when we actually have base fees and smaller fees, smaller payments. But that's a different discussion. I don't want to fall here, but yeah, James.
Just wondering, like, if I do AMP and I have one channel along one rack closes,
Yeah.
do the other? What happens then?
It's no big deal. That's a really cool thing about the design of Lightning. Remember yesterday we already had this, like, I was surprised that this was a frequent misconception, and I think it was not really in the room, but we discussed it. If on a route a channel closes, the other HTLCs are still settled off chain. Right? So also in AMP, if some of these things breaks, I mean, it closes, it has a long time lock. Right? So if the other stuff like works out and we release the pre-image, yeah, right. But again, I mean, these paths have to wait anyway all the time, right? So what AMP will or might do or could do, right? I mean, this is all speculation anyway because we haven't built this and we don't know this. But what I'm saying is the danger of AMP is that payments now have a really good likelihood of always take 24 hours or whatever, right? It's not lightning fast anymore because it's sufficient that one single path is taking your time.
Is there a way to do a redundant AMP where you have two more that somehow never claim more than 10?
Yeah, so you, well, I mean, one thing you can do in Lightning already is you can overpay a little bit already to obfuscate some stuff, right? So you could say, well, I'm willing to overpay a little bit. I have fees anyway, so I make a couple paths more, maybe like 1% or something, right? And in this case, if one path fails, the recipient at some point in time says, well, I have enough payment now, I release the pre-image, right? And with the rest, whatever happens, right?
So then you're only trusting the recipient.
Yeah. So I mean, for all of you, yeah? Payment hash? Currently in the suggestions, yes. But I think when we go with payment decorrelation and stuff, we could also like come up with ideas. But as I said before, remember this picture, right? It's very open. We can be very creative here, right? So if you currently think, oh, there might be a way of making different pre-images, right? I mean, you can simulate AMP already. You can already say, hey, I want to pay a merchant, and I really trust that merchant, right? I don't trust the payment provider, but I trust that merchant. Because the merchant sits in Australia.
Yeah.
But
knowing Rusty Australian people
no, but what I'm saying is, of course, you could simulate AMP already and tell the merchant, hey, please give me €1 in or $1 invoices, and you pay one invoice after a time, right? And if one of those got stuck, you'd be like, yeah, come on, do another, right? You could do that technically, and then you have different pre-images. Right?
The payment hashes are different in the sharded AMP.
So there's many AMP proposals floating around, as you know, right? And I think one of the reasons why many proposals are floating around is because nobody came up and said, hey, by the way, this is a really good solution for pathfinding, and everybody else said, oh yeah, we agree, it's very obvious that this is a good solution, let's go for it, because we're currently figuring this out. And as I said before, that's a great opportunity for you, having learned about all this stuff, because you could actually work on these issues. On the next slide, I will show a small table to argue that it's not even clear if the likelihood for successful payment is higher when you split those payments. So keep this for a second. Another disadvantage of AMP is you have more HTLCs in flight. I think we discussed this yesterday already in the room a little bit. When you make more payments, and those payments tend to be longer because you have to wait for the longest path, more HTLCs and more payment channels are in use, which could result in several things. One thing is, and I think I have this as points here, yes, statistically, we waste more block space if channels break. Because statistically speaking, the chance is higher that on these channels there are currently more HTLCs. These HTLCs usually are also smaller. The fees might eat up a lot of stuff, and the channels might become overloaded. Right? So remember, a channel can only have 483 HTLCs. Let's assume we make really, 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 really small payments. Then we're going to like eat up a lot of HTLCs. So we have to think about if we want to do that. Okay, and for improvements for AMP, I kindly refer to the talk of Alex that he already gave and discussions that we do outline. So again, I don't want to like say AMP is a bad idea, but it has some problems and we should be aware of these problems, right? I promised you to talk about and the question if actually AMP has a higher chance of routing a payment. And I have to say these are really completely arbitrary, not cherry-picked probabilities that I used in this one. So what I did is I said, well, let's assume the probability of success for a large payment is only 20%. And the probability of a small payment is 80%. And I don't even know what small and large actually means, right? But I thought 80-20 rule is always a good thing to start with. And again, it's completely arbitrary. So the AMP success probability is you take the probability of a small payment, and this has to happen for every small payment, right? So you have to like basically compute this exponential. And you ask the question, is this really bigger than the probability of a large payment to fail? And obviously better you do a simulation and you do whatever, right? I mean, this is just a really rough thing. Sorry for the transition here. You come up with this table. So here, this probability is always fixed. And this is the number of paths that I would use in atomic multipath routing. And obviously, if I only do one path, it's the same, right? For two paths, I didn't go directly to 80% because it's still a fairly large payment. So I went to 0.4, 0.6, and from there on, I said it's always 0.8. Probably it might be, like, again, I mean, it's just rough numbers. But what you can see is there's only a small window in which you actually get a higher probability with atomic multipath routing in comparison to just use the standard large payment. And in this small window, don't take this serious now because all the numbers are completely arbitrarily chosen, right? But if you think about it, it's not even clear. There's counter arguments to what I'm currently presenting, obviously, right? Because this formula is not really true. Right? If one path fails, well, you just probe another one. In atomic multipath routing, so eventually you might get it because you already have like a large fraction. But there might be really constraints on the global view of the network that really hinder you to find a path even with atomic multipath routing. And it's not even clear when this fails. Yes? Okay, so JIT routing. JIT routing is just-in-time routing. It's the following idea. Let's say S wants to make a payment of 90 Satoshi to R. And this is how the network currently looks like, right? So S and B have a channel of a capacity of 110 Satoshis. They're never that small in Lightning, and S has a balance of 100 Satoshis. And B has a channel with R that has a capacity of 200, but B only has 80 Satoshis on this channel. And then B also has a channel with T, also the capacity is 200. The balance for B is 80, and then here's another channel which is evenly balanced. Everybody has 100 Satoshis. Right, so what you can already see is when you probe this network, you don't find a path. Right, because here you can't forward 90, and here you can't forward 90. And very obviously, you can do it with AMP. Right, you can just do a certain split in AMP, and then you find the solution. What I'm trying to do in just-in-time routing is this picture. So when the onion So S selects this path over B to R. That's the path that S is really probing and doing. When B receives this onion, B says, I cannot forward this onion. In a regular payment, B would now send back an error and say, I can't forward this onion. All the HTLCs go all the way back to S and nothing happens. But B could now say, well, we do something, and I think I wrote this down here. Sorry. What B could do is, B could use one of the coolest tricks that we use in Lightning. What is the coolest trick that we use in Lightning in general?
Crash.
Rebalancing.
Yeah, rebalancing is the idea, but what is the concept, what B does now?
Oh, sending it yourself.
No, okay, I just give you the answer. B is deferring the routing process to the future. Right? And remember, Lightning, deferring publishing a Bitcoin transaction to the future was a good concept. Right? So we're doing the same here. B says, instead of sending back an error, I do what you say, you rebalance. Right? So now B does a circular onion, sending 50 Satoshi on this channel, only having 30 now. This one also moves some capacity on the channel. Now there's 130 Satoshis on the channel. And what you can see, the payment went through. Great.
So would you want to increase his fees dynamically, given that he now has to?
Well, that can't happen because the onion is already constructed.
Right. Yeah.
That
The
can't
onion
happen.
should just contain some redundant fees then, so that others can do these little.
I mean, that's a question, right? I have different suggestions to mitigate this problem. My suggestion is that I have this on the slide.
Sokoban routing, by the way.
Hmm?
I call this Sokoban routing.
Yeah, okay. No, I call it just in time because you get your liquidity that you need just in time, like the Toyota supply chain concept.
What happens if I cancel the receiving of the payment?
If you can't solve it,
If I cancel my receiving, I don't accept it. But
who are you in this graph now?
if I'm getting the payment and you do the just-in-time routing,
Yeah.
but I just, when the payment comes to me, I just cancel, I reject it.
Well, that's no big problem because if you read on the mailing list, a person suggested that you can do the rebalancing with the same payment hash. And in that case, the rebalancing only takes place if you accept the payment, so you only pay fees for the rebalancing if the payment
Oh,
goes
No,
through.
in that case, you still don't have enough capacity to go through ER.
Because you already are here, right? I mean, in that particular graph.
No. Because if you bind the rebalancing to the same pre-image, then the HLCs will not get resolved, and you can't create a new HLC for 90.
No, but here, since you have two HTLCs in two directions, they could have a protocol of mitigating this.
Oh.
You could. I'm not saying we should do it, I'm saying you could. But I even have a different suggestion for this. So in general, my suggestion is the peers might want to omit the fees on the rebalancing operation. Right. So in general, if you look at graph theory, there is a certain amount of networks you should always look at when you look at a graph. So there's one thing that is called your ego network. That is, if you're B, your ego network consists of S, T, and R, right? Everybody who is around you. And I mean, that's the network that you usually know in Lightning very well, because you have your node and you know what's with your channels and your peers. But what I would suggest is to look at your friend of a friend network. So if I am S, my friend of a friend network actually goes all the way to R, because all the friends of my friends are in there. And if you do the math, you will realize that all circles of length 5 are in your friend of a friend network. So what if, and that's a question, what if we would argue and say, you know what, in your friend of a friend network, we introduce another gossip query or another query of saying, hey, to all my peers, give me your channel balances of all your channels right now. Then I have a very local view where I actually know the exact topology and I can suggest a rerouting, a rebalancing route. And I could even do it public, right? I could extend the bold protocol. And everybody on this route would say, hey, actually for each of one of us, it's better to now shift these funds. So now you can do the rebalancing for free. You could, right? I'm not saying we should do it in this way, but I mean, this is one way of achieving this. And if you compare it with the privacy model of Trampoline, it might actually be a better privacy model. And you don't have to do it as drastic as I'm suggesting this right now. I mean, you could also have a query of saying, hey, tell me channels on which you want to have inbound capacity, or tell me channels on which you want to have outbound capacity. I just continue. So some considerations with JIT. I think the idea got clear. So the disadvantages, you need additional probing for the rebalance operation. It may be costly for routing nodes, right? Especially when you do it on the current system, because you just have to pay fees, and maybe even for the rebalancing use a different pre-image, because currently that's easier. The CLTV deltas currently might not be sufficient to support an additional routing operations because they're very tight on time, and you don't find a route that actually completely works on smaller CLTV deltas. And it also increases the time because there is a time needed for rebalancing. Again, as I mentioned, one way of improving this is of creating this friend-of-a-friend overlay network and maybe extend the gossip protocol here to exchange a little bit more information. Similar in this like BGP setting, we could use some aggregated information about the channels to do this. And we could do cost-free circular roads in Lightning. Especially if they are not encrypted, you know that you can't use them for like denial of service attacks or something, because you know who is involved. All right, multi-hub trampoline payments. So the high-level idea, I think we already saw it. You get the best effort component in. You define a rough route if you do multi-trampolines, where you say, hey, it should go through these trampolines. And then let the node on the route figure out how to do the actual paths between the trampolines, right? So again, you shift this like pathfinding problem to those people who are along your route. So I think yesterday the idea was coming up, but not very clear, that it might make sense on Lightning to extend the gossip protocol, that the trampoline nodes have like their own network of saying, I'm pretty confident that I'm able to like forward to Christian, even though we're not direct peers or something like this. So then on this like trampoline network, I could make a route, right? Somebody in their invoice could say, hey, use this trampoline as an exit trampoline, kind of this thing, go in this way. Disadvantage is it needs a protocol change currently. We need these mixed onion formats, which is always a little bit, I mean, I think it's coming, but we need it, right? So yeah, the onion format needs to adapt it. A click of trampolines, that is, in my opinion, a more severe problem, might emerge and build a cartel, right? Especially if you even enforce something like this on the protocol level. So there could be, I think the question was already coming from the room, centralization or hub and spoke topology might emerge, and the privacy model decreases a lot because the trampoline really knows I'm doing a payment to somebody else, right? Or somebody's doing a payment to somebody else. Whereas in JIT routing, you don't have this problem, right? The person initiating the rebalancing just knows, like before, from where to where on the local view, but not on the global view. And I think yesterday we kind of figured out that it wouldn't work for all, at least right now, for all spontaneous payment protocols. So for improvements, I refer to talk to Christian and probably also to Pierre-Marie Nebastien is working on it, right? Okay, so just to sum up some general thoughts on pathfinding, I think we should acknowledge how I already did in the other talk that pathfinding is an open and difficult problem for the Lightning Network. We should not ignore this. And I personally think we should not wait to tackle this problem, right? I mean, you could argue currently the Lightning Network is small and our current mechanism works. But if we need severe protocol changes for some of these ideas or for even other ideas, then of course it might be too late once the Lightning Network is already widely spread. So I think this is really a problem we should like quickly work on. Various proposals and ideas exist. Some of them require protocol changes, and different strategies could be combined. I want to emphasize this, right? You could combine trampoline payments with JIT routing, with AMP. You can combine AMP with JIT. You can do all of these, right? It's not like one algorithm wins, maybe. Maybe it does at the end. And there seems to be a trade-off between these strategies, right? Some have like more privacy of individual nodes or the ability of the network to solve the pathfinding problem. It's like really like, where do we want to stand on this? And yeah, I say Lightning might want to copy some ideas from the autonomous system space. In particular, I think it would be really useful if we have this hierarchical address space, or as Christian suggested, to have like a core open routing protocol on the base that always works, and then create an encrypted layer on top of this right? Because this will just increase the success rate, and not everybody is desperate for privacy anyway. My personal opinion is that pathfinding, as I mentioned before, will emerge as a business model and opportunity, because if we keep it with this current setup, then people with third-party services will definitely win, because once you offer that service, you easily might have more information than other nodes on the network, and then you can offer better paths. Why do you have more information? Well, I think it's similar to the Google setting, right? Everybody can now set out and write a web crawler and have like a view of the web graph, but Google has all the log files, and the log files are a crucial piece of information that help Google to make better search suggestions. So I conclude my talk by saying pathfinding has many challenges. So please tinker about them, join us, and take this problem serious.